versus what happens if a silicon atom gains an electron? What's going to be the charge on this? It'll be negative now, right? Because now we're talking about the affinity for electrons. We're talking about what is the likelihood that the atom wants to gain an electron. All right. So if I drew out the electron affinity or electron being gained by silicon, it'd be Si plus an electron goes to Si minus. Right? So it's the opposite of ionization. It's you're taking, instead of taking electrons off, you're putting an electron in. And there is a delta E associated with that, and we call that the electron affinity. All right. So let's look at the orbital diagram. So we have 3s, 3p, we'll just do all these, right? We got chlorine, what's going to happen when chlorine gains an electron? What charge is going to be on chlorine? It'll also be -1. Yeah, so we're talking about when we say electron affinity, you might see EA1 or EA2, meaning the second electron, right? And we also have magnesium, and we have phosphorus, lithium. Magnesium minus would be, I'm just going to compare and contrast here, P minus, and then we have Na minus. So we look at silicon. Okay, how do I fill this in for silicon? 3s2, 3p2, right? Okay, and then silicon after is going to be, it's going to be minus, it's going to have a 3, the half shell, right? Alright, let's just do all the neutral atoms here. Oops, this is magnesium. Getting kind of happy with electrons here. So there's our neutrals. Here are our negative versions. All right. So is silicon gaining an electron going to make it happier? Or is it going to make silicon less happy? It's going to make it more happy. Because silicon, when it gains an electron, all right, when this happens, this is more happy. Chlorine gaining an electron. Is that going to make chlorine more or less happy? It's going to make it more happy because all of a sudden again, oh hey, I get a full shell now. So again, more happy. What about magnesium gaining an electron? Now it's less happy. Now it has to put an electron in a higher energy subshell, right? That makes magnesium unhappy. So I'm going to say less happy. Okay, phosphorus going to phosphorus negative, more or less happy. That's also going to be less happy. If you have an English accent, you'd say less hoppy, and hoppy means something else in the making of beer. Hoppy. Okay, anyway. Let's see. Sodium gaining an electron, more or less happy.
More.
Yeah. Yeah, more happy. So we have 2 lesses and 3 mores. Now in general, as you go across a row, the electron affinity will increase. But when you have neighboring atoms in the row, this is where the nuance comes in with the half shell, full shell concept. So if we just drew or wrote a general trend, going from more or less. So if you look at the row, it goes sodium, magnesium, then silicon, phosphorus, and chlorine in that order. That's just the order in the row. So normally, let me write it over here. So let's see, we have sodium first, followed by magnesium, followed by silicon, followed by phosphorus. So you would think that this would be the correct order of increasing the electron affinity. In other words, it releases more energy to the surroundings for chlorine to gain an electron than the others. In general, this is the correct trend, but these are out of order a bit. How are they out of order? Well, let's look at this. So if we compare sodium and magnesium, does sodium want an electron more than magnesium does, based on the half shell, full shell rule? Which one wants an electron more, sodium or magnesium? If sodium wants an electron slightly more, although I'll tell you, in general, the metals just don't want electrons, but if you had to compare sodium to magnesium, it's a little bit easier to add an electron into a sodium atom than it is to magnesium. All right, and again, the reason being is because by adding an electron to magnesium, you've got to add that extra electron in a higher energy 3p subshell now. Okay. So it turns out that we got to reverse these two. Let me just rewrite the order down here. We got to reverse these two in order because, again, less energy will be released when we add an electron to magnesium. Okay, or in other words, it's harder to add an electron on magnesium than it is to sodium. Sodium compared to silicon, though. Is sodium close to silicon in the periodic table? Not really. Okay, so we would still say that silicon is going to be higher in electron affinity relative to sodium. Now the question becomes, how does silicon compare to phosphorus? Because those two are next to each other in the row. Which one wants an electron more, silicon or phosphorus? Silicon wants an electron more because it has 2 electrons in that 3p subshell. By gaining a third, it now gets to a perfectly half-filled subshell. Whereas with phosphorus, if it gains an electron, you can see that it now becomes more than half-filled. That makes phosphorus less happy, right? So we're actually going to go ahead and reverse these two. Now, does phosphorus want an electron more than sodium? Yes, right? So again, phosphorus is so far from sodium that they're not comparable. So we're just looking for elements that are close, that are next to each other in the periodic table. We're not comparing elements that are more than one away. And then, of course, the chlorine, that really wants an electron bad, because if it gets one more electron, it becomes like neon, right, or argon, right? So that's still going to be the highest. So the correct order would be this bottom one, this bottom array. So this is not the correct order, this is the correct order. So any questions about electron affinity?
So you want to put them in order first and then compare them side by side, the ones that are next to each other first? Okay.
So you can see with all the periodic trends we discussed, atomic radius, ionization energy, electron affinity, we're kind of taking things and putting them in the overall trend first and foremost. Okay, I could have placed these in the arrow diagram just like I did the others. Okay, and I would have come up with this order. Okay, but again, the half shell, full shell concept distorts that a little bit. So in Chem 107, they didn't really talk about the half shell, full shell concept, when it came to ionization energies. At least I don't think they did. You might not remember. Well, yeah, people are not even like, I don't remember that from Chem 107. So, and I don't teach in 107 either. So what are the three periodic trends that we've talked about? Atomic radius, ionization energy, electron affinity. All right, and so use the box diagrams I gave you to work through problems related to this, and then pay attention to the half shell, full shell rule in addition to that, and that should complete the picture. Here's an example of how electron affinity affects reactivity. If you take hydrogen gas and react it with the halogens to produce a hydrogen halogen gas. So for example, if this was fluorine, this would be hydrogen fluoride gas. If this was chlorine, it'd be hydrogen chloride gas. If this was bromine, it would be hydrogen bromide. If this was iodine, it would be hydrogen iodide. Getting back to your nomenclature, always there, right? Okay, so what kind of reaction is this? It's a combination reaction, which makes it, which one of the three main reaction types? It's a redox reaction, right? So if we look at the oxidation numbers, I really like talking about this stuff because it ties in old ideas with new stuff, okay? So you take hydrogen gas, react it with, say, fluorine gas, and you produce 2 hydrogen fluorine gas. All right, let's look at the oxidation numbers. What's the oxidation number for hydrogen gas? It's a free element, it's a diatomic element at 0. Fluorine, what about that? At 0 as well. Then we look at the HF. What are the oxidation numbers in HF? H is +1. Okay, H is +1, and fluorine is -1. So in this process, is the fluorine gaining or losing electrons? It's gaining electrons, right? So it turns out that when you look at the reactivity trend of hydrogen with the halogens, it turns out that the reaction goes much more violently with fluorine than it would for chlorine and bromine and iodine, right? So you see this reactivity trend, the exothermicity, delta H of that reaction, and you do that for all the other halogens, you'll notice that the exothermicity increases, the enthalpy gets more exothermic with fluorine relative to chlorine, which is more exothermic relative to bromine and so forth. Okay, why is that? Well, if you look at the oxidation numbers, the fluorine is gaining the electron, right? That's the electron affinity taking place there. Okay, so the fluorine is gaining an electron, its electron affinity is greater than it is for chlorine, which is greater in electron affinity relative to iodine and so forth. That make sense? But as it's like, yeah, sure, what did you say? Right? So what's going on here is hydrogen is becoming H+, but fluorine is becoming, fluorine is gaining an electron, right? So this is the electron affinity for the halogen. This is the IE for hydrogen. Now hydrogen is always the same in all these reactions, right? So the only difference is, you know, if I do chlorine, right, which one is going to be more exothermic? I think we're meeting up with brain fry stage right now at this point. We'll stop right after this. So again, fluorine gaining an electron. Okay, which atom wants an electron more, fluorine or chlorine? Yeah, fluorine wants electrons more, and the reason why is because it's a smaller atom. It has less screening, so an electron that would come in has less screening to deal with to be trapped by the nucleus at this point. Okay, so it wants electrons more than chlorine does. The electron affinity, therefore, would be greater for fluorine, and this is why this reaction would be quite violent compared to the other halogens. Wouldn't want to be there. Actually, I would, but just for this. All right. So that finishes chapter 8. And we can meet up upstairs.